Okay, Year 12, last chapter of the textbook, and it's a weird one. It's a lot of miscellaneous topics put together, which you could say for all of Module 8, but this chapter especially. So the textbook has called it Chemical Synthesis and Design, so there's a little bit in there. Maybe I should talk about this. So we're talking about, or the last part, implications for society of chemical synthesis and design. So there's one syllabus point. We're evaluating factors that need to be considered when we're designing chemical synthesis process, or we're making stuff chemically, and usually industrially too. Okay, so we need to talk about these things: availability of reagents, not too much, reaction conditions. We've already talked a lot about that, and it still goes back to Le Chatelier's principle as well. Le Chatelier's principle. Yield and purity are new, but they're little kind of tacked on subjects, which we'll talk about first. And the real big thing here, because we haven't done much of other stuff, we've done a lot of the other stuff. The other thing here that's kind of tacked on to the end is the environmental, social, and economic issues that come with making chemicals. So let's just revisit synthesis reactions. Remember how we started Year 11, we said that a synthesis reaction is when you have one product for two or more reactants, so X plus Y going to Z, okay? Chemists don't always use that definition, but synthesis reactions, and when we're talking about them, we're aiming to make a special product. There's a product. There may be more than one product through our reactions, but there's one particular product that we're hoping to make or synthesize, okay? So there don't need to be technically the old school definition of a synthesis reaction, where you've got one product. You could have other products, but we name them usually byproducts, okay? We want to get rid of them in the process, take away the byproducts, and we're looking for one thing that we're hoping to make specifically, and we've kind of already done this when we do esterification. Okay, so esterification, we're reacting an alcohol with a carboxylic acid, and we're making an ester and water. Ester is what we want. Water is the byproduct. So we're hoping to synthesize an ester, and the reaction conditions are how we aim to shift it to the right hand side using Le Chatelier's principle. And the conditions for it. So the conditions that we use for esterification is we want it to happen quickly. So we use a catalyst.
Hey, mate.
Thanks, mate.
Cheers.
And should I start this again? No, I'm just going to roll with it. So we use a catalyst to make it quicker, but to shift it to the right, we use excess of one of the reagents. And we have the byproduct of water. And remember, we go through that series of steps to get rid of any unused reactants, where we react away the acid catalyst and the carboxylic acid with sodium bicarbonate, and we extract the organic layer. We do the separating funnel, those type of steps. So that's a good synthesis reaction example, making an ester, and it comes up all the time in past HSCs, okay? So that's a really good, hold it in your back of your pocket for if a question goes, talk about a synthesis reaction and all the implications of, byproducts and purification and all that kind of stuff. Esterification is great for that. Other ones we've studied, we've also talked about bioethanol and biodiesel, making those, and we've also talked about the environmental and social and economic impacts of those, so we've kind of already covered that. We've talked about making soaps and detergents. We haven't done it practically, but we talk about it. We've talked about before the production of ammonia through the Haber process, but later on in the chapter I'm giving you a bit more of a chance to go in more in depth. And also methanol as well. We might have touched on the contact process, but later on in this chapter we'll pull that up as a case study as well. I've also talked about the synthesis of polymers too. So I've done a lot of synthesis reactions already. And all throughout we've talked about we talked about a lot of polymer the social implications of using polymers and plastic waste already. Okay. All right. Let's see how I've written here. Okay. So many synthetic products. So many of the type of chemicals that we want to make, especially in pharmaceuticals, take their inspiration from nature. Okay. So early pharmacy was based on sophisticated trial and error methods. Remember when we talked about indigenous people eating and trying cycads and the processes that way they went through to do that? Same type of process that all peoples have used over time to find out pharmacological effects of different things, okay? And over the millennia, we've kind of built up that knowledge by word and stuff, and it's become known as traditional medicine. So in the 20th century, chemists have developed means to determine the structure of these molecules that we're talking about that are in traditional medicine. So we've gone and we've found, hey, this traditional medicine says this, let's try to find the active ingredient or the molecule that's doing that, and we can use our analytical methods like NMR and stuff to find out the structure and then actually synthesize that. And that's what we've done, okay? So here's my example. It was known that willow bark, so the bark of certain willow trees, is known to relieve aches and pains and fever, and it's been known for millennia. So chewing on the willow bark, yeah? The trouble is that it often came in the olden days with the side effect of stomach cramps and pains, okay? So what happened in the 20th century, we come along and we've determined the active ingredient in the willow bark was salicylic acid. And here's a structural formula for it there. It's a benzene ring with a carboxylic acid and then an alcohol off it. And we've called it salicylic acid since. And we know that a side effect of using the salicylic acid just by itself without the bark, people still get the stomach cramps. And it's usually from the stomach being too acidic. And you get that. I don't know if you've ever done it. I've only done it once in my life where I've drunk a whole heap of orange juice. And the stomach cramps that you get after it. I'm talking about 1 or 2 liters here. I was young, stupid. Don't do it. So one of the big pharmaceutical companies now and also in the 20th century, Bayer, what they did is they trialed different variations of the salicylic acid, and they came up with this other one that we called during the older naming system acetyl salicylic acid. So notice how instead of the alcohol group, we've now got this ester group on here. So they did an esterification on this alcohol, and they got this other compound that they found, and they did trials, they found it has exactly the same pain relieving effects, but it's not as acidic as the salicylic acid, and they marketed that as the brand name aspirin, okay? And it's one of the largest, and has been one of the largest selling drugs on the market, okay? So they found inspiration from nature, they changed the molecule slightly to get rid of effects, and now they're not growing willow bark, they're making this molecule from smaller molecules, okay? So, talked a little bit about this, but we'll go into it more. Designing synthesis reactions, okay? Here we're talking about, we've already kind of done this. So designing reaction pathways, knowing our organic reactions that we've learnt. And here's a general kind of diagram. So more general reaction pathways can be drawn up to help plan specific pathways. So this is stuff we've already learnt, how to shift in between, how to take an alkene and do polymerization or do addition to make a haloalkane and all these different stuff. So choosing the paths to make what you want, okay? Designing synthesis reactions. And here's some more. Here's a more specific one. Notice how that's very general. If you want to take an alkene to an alkane, well, you're going to do an addition reaction. Here's something more specific where they've got, if you follow the arrows, they're all kind of going around this way. But so that what they're making is they're trying to make this alkyl ethanoate, or they're trying to make an ester, aren't they? An ester with an ethanoate end. Okay, they're making something ethanoate. let me get rid of my scribble. And so what they've done there is working backwards, they've gone, oh, I need ethanoic acid to do that, and I need some kind of alcohol as well. So they made the ethanoic acid from ethanol, and they oxidized it, okay? And they made the ethanol from a substitution reaction, yeah? And between the chlorine to the hydroxyl or the alcohol. And they made that chloride on that methyl group by doing a substitution reaction with ethane. Okay, they're also recognizing that you could do ethene to go through here as well. I think they might be talking about making the alcohol. Yeah, so that's more of a specific. Okay. So there's two main ways of designing reaction pathways, and notice in that last one, I went backwards. Okay, I looked at the product that they wanted and I followed the steps backwards. That's a very powerful method that's used in chemistry, okay? Instead of starting with, hey, I've got these building blocks, what could I make? One thing that chemists do is they go, I need to make this molecule here. And so here we call it the target molecule if you want to do that. And here we work backwards and go, one little kind of functional group at a time. How do I add that on? Oh, I could start with the molecule like this that is just one shift away. So here with this target molecule, they went one shift away. And what's one shift away? They went, oh, there's an alcohol group on there. I could add the alcohol group through a substitution if I had a halogen on there, okay? And so they've gone back one step, or they've gone one step back in this retrosynthetic pathway. Retro meaning backwards, okay? Moving backwards synthesis. So they're like, oh, I could do hydrolysis or substitution reaction with a bromine there. So, okay, so I could start with that one in the step before. So I'm going to call that an intermediate, okay? But I could go back a step to something simpler, okay? If I can't buy that off the shelf, I could go back and go, well, how do I, one step back, how do I get that bromine on there? Well, I could do a substitution reaction there, okay? And so they've gone and got rid of the bromine and started from there. So they've gone back to a simpler reactant on each step, okay? So here it's just 3. They've only got their target molecule and an intermediate, and now they've got their starting one. And so they're saying starting, we can easily buy, methyl propane off the shelf kind of thing, if you want to call it that. We can easily buy methyl propane off the shelf, but we can't buy 2-bromo-methyl propane, and we can't buy 2-methyl propanol. So you can't buy those, but you can easily find something, a building block that you can start and then move along. But they've analyzed it and worked backwards, okay? And so this is called retrosynthetic analysis. Okay, this is a very simple one. Most retrosynthetic analysis are very multi-step, okay? Looking at complex organic molecules, say, well, there was a few chemists that I used to work with who did research like this, making pharmaceuticals that were found in nature. So I'm trying to remember, one of them, she was doing some molecules that were made by sea sponges, from memory. They were large complex molecules that had a lot of functional groups on there. But what she'd do is she'd analyze and find those molecules from the sea sponge samples, run them through NMR and get their structure, and run them through IR and make sure, all those organic analysis to get the structure down. And then she'd do retrosynthetic analysis on them. She'd take one functional group away at a time until she got something or a series of reactants that she could buy off the shelf, okay? And do several multi-step reactions, okay? So she was probably looking about, 10, 20 steps to do hers, so it's just more complex, but it's the same idea. She started what she wanted with, and she just took it back one step at a time from a series of reactions that she knew. So it's determining the reaction pathway in reverse, okay? So another thing you've got here is this one here. It's very linear. It's this step, then this step, then this step, okay? So linear reaction pathways take take a reagent and make it more complex in each step, okay? So A to B to C to D to F. It's very linear. So here's an example of sulfur with oxygen making sulfur dioxide, reacting with oxygen, making it sulfur trioxide and sulfuric acid. And then, this is the contact process that we're going to talk about. I forget what that guy's name is called, and then water, and then we get to all the sulfuric acid. You've also got like branch pathways or convergent synthesis, okay? And here, our best example is if you're making, from scratch, I'm going to call it an ester, okay? And so here we've got ethyl butanoate. If you go backwards, well, you need an alcohol and a carboxylic acid. Notice it's split. And to make that ethanol, you're going to take ethene and water. And to make the butanoic acid, you're going to oxidize butanol. And you're going to make the butanol from so you're going to do addition of water across a double bond. So that's a convergent synthesis. It's taking two or more pathways to make two or more reagents and bring them all together at the end. Okay? So that's about as in-depth for synthesis as we go. You've got some tools to do this very simply. There won't be too hard questions in the HSC. The next little topic that we're going to tack on here is something called yield or reaction yield. So the yield of a reaction is a proportion, and it's usually expressed as a percentage, of how much actual product you get compared to a theoretically calculated amount. Okay? So we've previously looked at limiting reagent problems, okay? And what we've actually been determining is something that we're now calling the theoretical yield. So for example, we've got a problem here. If this mass of zinc was reacted with this many moles of HCl, what mass of hydrogen, so what amount of product could be produced, okay? We've done lots of those problems. What could be produced is now what we're calling the theoretical yield, okay? If we're assuming that all the reactants come together and the limiting reagent limits the reaction, how much could be produced? That's the theoretical yield, okay? However, real life, okay? Real life chemistry is a lot more complicated than that. When you actually do take those masses and all that and you put them together, quite often you don't get what should be produced, okay? So what you're actually getting, if you physically do it and you weigh it out, you're getting an actual yield, okay? We never truly achieve the theoretical yield, and there are many reasons why chemically. Please don't say human error. That will make my head explode. We can go a lot deeper than that. And it does go beyond and a lot deeper than that in your future chemistry career if you choose to go tertiary. What we do achieve, though, is an actual yield, okay? So it's well known with certain reactions that actual yields can be certain low percentages, especially in organic chemistry. We know going in with the best conditions that we have that an actual yield for a reaction is somewhere around, let's choose, it's just arbitrary, just around 20%. But we know that as scientists going in, and we try to push it as much, but we can only push it to 20%. We take that into account when we're doing these reactions industrially. Okay, so the percentage yield of a reaction, how you calculate it in a problem or a series of reactions, it's the ratio of actual yield over theoretical yield multiplied by 100%. How much you actually get determined by how much you should have got times it by 100%. Let's do a problem, okay? 128 grams of sulfur dioxide was reacted with excess oxygen and produced 108 grams of sulfur trioxide. Calculate the percentage yield, okay? So if I'm calculating a percentage yield, what I'm looking for is I need to calculate the theoretical yield and hopefully, well, they should have given us an actual yield. So they have given us an actual yield here. Maybe I should highlight. actual yield they've given us here, and we can calculate the theoretical yield from the information given in the question. Okay, we've got our 128 grams of sulfur dioxide and other information, excess oxygen. Okay, let's start with a balanced chemical equation too, because that would help out. So we've got sulfur dioxide, which is a gas, and we've got oxygen, O2 gas, before I put the comma, and we're going to sulfur trioxide from the question. Okay, let's balance it out. Oh, we need 3/2 of that one, so we need two of those, and so we got 6, 4, 6. I think that's good, isn't it? 2 sulfurs, 6 oxygens, good. Okay, so info from the question, I've got 128 grams of this guy. Here we've just got excess, okay? So we know already that the sulfur dioxide is going to be the limiting reagent because we've got a whole heap of O2. So we know that the theoretical yield is going to be based on the amount of moles of the limiting reagent, which in this case is the sulfur dioxide. So let's work out how many mole of SO2 we've got. 128 grams divided by 32.07 for sulfur, plus 2 oxygens at 16 grams per mole each. I have my calculator. I'm going to put it in. 128 divided by bracket 32.07 plus 2 times 16 gives me 1.997 for blah 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 moles. Okay, that's the limiting reagent, sulfur dioxide. So we can just go, well, theoretically that will make how much sulfur trioxide? SO3 moles is going to equal the number of moles of our known moles of SO2, multiply it by the fraction. SO2 is on top, we want it, the moles of it on the bottom. What do we want to introduce? SO3. What's the stoichiometry in front of each of them? What's in front of the SO3? 2. What's in front of the SO2? 2. So 2 on 2 equals 1. So we're just looking for so we just could produce the same number of moles. So it's going to equal 1.997814 mole of SO3 produced. Okay? Convert that over to a mass. Okay, 1.997814 moles, times it by the molar mass, 32.07 plus 3 times 16 grams per mole. And then it's going to give us our theoretical mass, or our theoretical yield. 32, I kept my number in my calculator, plus 3 times 16. It's going to give me a theoretical mass of 159.965 grams. So this equals the theoretical yield. Okay, I'm going to move my box up in that space. So my percentage yield equals actual yield over theoretical in grams times by 100%. So for us now it equals, our actual yield from the question was 108 grams. Our theoretical yield was 159.965 grams, and we're going to multiply it by 100. Okay. Kept my number in my calculator. 108. I get 67.5. Yeah, I'll keep it to 3 sig figs. We're where am I going? 67.5% to 3 sig figs. All right. I'll keep going here. Sorry, I'm just having a browse. So, factors that will reduce an actual yield are usually matters for us in this simple. It's usually matters of equilibrium. Okay, so we've got a callback. So we need to design a reaction pathway that would involve designing the conditions that maximize the yield. Okay, so we need to implement Le Chat's principle to push the reaction as far as it can go. So a couple of things, just a bit of a revision. We could remove products. So you decrease the concentration of a product, the forward reaction is favored. We can choose the appropriate temperature. Okay, so choosing high or low temperatures based on whether it's endothermic or exothermic process. Okay, so treating heat as either a product or reactant and using Le Chatelier's rule there. Also pressure, if you're using a gas in there, you could consider high or low pressure to favour the side of, when we're talking about gases, high pressure will favour the side of least molecules. And also you can also recycle a reactant. So unused reactants, you can put them back in the reaction vessel, driving the forward reaction. And it also reduces waste as well. Okay. Also, another thing to consider is that some of these reactions take time, okay? So it's not as if, how do I put it? You want to get the highest yield in the shortest time sometimes, okay? So remember back when we were learning about the effects of reactions, and we learned about catalysts, and we said catalysts don't shift the equilibrium. All they do is help you get to the equilibrium quicker, okay? So remember, a catalyst is not going to increase our yield for the reaction, but if you don't wait for the reaction to reach equilibrium, it's going to increase the yield in a certain amount of time. Okay? I don't know if I'm explaining that right. Say if a reaction takes 3 days to occur, okay? Put a catalyst in and it could reach 2 days to occur. But say you wanted to do it on a daily basis, okay? Say if you wanted to get your yield every day in the afternoon you wanted to pump out your yield, you'd put the catalyst in, and although the reaction hadn't finished, the yield that you're getting on at the end of day 1 to pump away is a greater yield using the catalyst than if you weren't, okay? So it's giving you a greater yield in a shorter amount of time if you're not reaching equilibrium. So a catalyst is often used to increase the yield in a shorter amount of time, okay? So be careful on that. A catalyst will not affect the amount once it reaches equilibrium, but if you're doing it in a shorter amount of time before it's reached equilibrium, it will increase your yield. Hopefully that makes sense. Okay, so we're just going to end on this one, and we'll finish talking about yield. All I've done is I've just changed this question. I've aimed for the same type, but I haven't said that one of them is in excess, so we've got a truly limiting reaction here. And notice also that we've said a time period. So I'm hoping that you recognize that, hey, shorter amount of time, maybe it's not maybe the reaction will take longer than this. So if I introduce a catalyst, it'll make it go quicker. I've also introduced some information about whether it's exothermic or endothermic. So part A, we're calculating the yield, and part B, we're proposing 3 strategies that would increase the yield, okay? So let's do percentage yield. I haven't given myself a lot of space, have I? Okay, small writing. Okay, nitrogen. And, oh no, it is excess hydrogen. I lied. It isn't truly limiting, is it? I've said excess hydrogen, and we're making ammonia. Oh, it's the Haber process. Okay, so balancing it out, we need 2 ammonias, we need 3 hydrogen molecules and 1 nitrogen molecule. Okay. Look, if I actually sit down and read it, it says produce. So there's my actual yield, and what I'm working out is my theoretical yield. So I've got 340 grams of nitrogen and I've got excess hydrogen. So I'm going to work out how many moles of nitrogen I have. 340 grams divided by 2 times 14.01 grams per mole. Put it in my calculator. 340 divided by 28.02. 12.13 moles. And because I've said, and I've actually read the question, that I have excess hydrogen, I know that the nitrogen is limiting, so moles of NH3 going to equal my 12.13 moles of nitrogen times it by my molar ratio of ammonia to nitrogen, 2 moles of ammonia to 1 mole. Okay, so I'm going to produce 2 times that. Theoretically, 24.268 mole. Okay, convert that into a mass. Times by the molar mass of ammonia, 14.01 plus 3 times, I was going to say 16, 1.008 grams per mole. Put in my calculator, times bracket 14.01 plus 3 times 1.008. So theoretically I can make 413.3875 grams. That's my theoretical yield. My actual yield was there. So my percentage yield, am I spelling yield right? E-I-I-E? It's I-E. I need to remember that spelling. So my actual yield was 268 grams over my theoretical, which was 413.38 blah 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 grams, times by 100. $64.8. Can I go? Or I can only go 2 sig figs because of the 340. So that's 65%. 65% yield. 3 strategies. Okay. I'm going to go back to and write in heat in my equation. It's exothermic, so heat is a product. Okay. So, according to Le Chat, let's do the heat thing. If heat is a product, okay, I want to drive the forward reaction, I need to take one of the products out. So I can take out heat. So another word of taking out heat is cooling reaction vessel. To drive forward reaction as it is exothermic. So there's one strategy. What else? We talked about the 6-hour period and the fact that catalysts don't increase the yield, but they can in a shorter amount of time. So we can say introduce a catalyst as time constraint is there. So here we can, as time constraint is present. So we can increase the yield in the shorter amount of time before it reaches equilibrium. What's another thing that we can do? Remove ammonia. Remove ammonia from reaction vessel. We could, well, I've already said we've got excess hydrogen, so we can't really add in more than excess hydrogen there. We've already done add in an excess of reactant, so we can't do that one. The only other thing I can think of is pressure, okay, because we've got a homogeneous gaseous reaction. 4 molecules on the left-hand side, 2 molecules on the right. So if I want to push it to the right-hand side, or the side with more molecules, I need to increase the pressure. So increase the pressure in reaction vessel. All right. Hopefully that's helped you out. You can do that worksheet on yield.